Good morning, people. I think this is the first time I'm taking an FIBA lecture from the college. Let me just wish you all, Sanmit, Sachin, Mayuri, Avi, good morning, Aishwarya, good morning, Sandeep, Ami, good morning, Rasika, Karthik, good morning, and Prajakta, good morning. Hope you all have enjoyed your Diwali vacations, a brief vacation, I would rather say. And as I said, mentioned earlier, I think this is the first time that for FIBA I'm taking a lecture from Ria, good morning, Anushka, good morning, from the college. Now, a few interesting things that we were doing last time. Now, there's some issue with my mouse and I'm not able to. Okay, yeah, got it. We will immediately start with what we were doing last time, and that was the interior of the earth. We rather were speaking about it, and if you remember, we started with the contemporary issues. What are the major issues that are there as far as geography is concerned, and how they are interlinked, and how the climate environment and is related to the society. Eventually, society is made of humans who are globalizing this world, and then the importance of geographic information systems, which would be there. That was what we were doing last time. Then we went into this aspect, the deepest places on the earth, and we went through a lot of interesting things within that, which included a scale of representing all these things. Okay, the deep mines as such, the mining, and of course the deepest open mining and closed minings and the canyons and etc. If you remember that, we were doing all that, and eventually we came to the cross section of the earth. Okay, and we went deeper from that upper mantle, lower. Of course, the crust, which you can see here, is very narrow, because it is just 40 to 60 kilometers, and then you have the upper mantle, you have the lower mantle, you have the outer core and the inner core. We are going to go into the details of these one by one, and by the way, we also spoke about these things which we had done last time, and then we went into this diagram. Okay, and this again showed us how deep, how high, okay, the relative heights. Now this is important to understand, basically because eventually we need to travel into the surface of the earth, and while we travel we need to connect it. Okay, how long, how far, how deep, and that is why I on purpose put these things together, so that we can understand how deep and how, where we are all about. Okay, so this is what we did last time. And then we entered this aspect that we needed to see the structure of the earth. We all remember and we know that as far as the formation of the earth is concerned, it was not a process which took place in a very small period of time. It took, I would say, at least hundreds of millions of years to solidify, because earlier it was gas of a ball of gas, and eventually you'll see that the gravitational force of the sun, and as it revolved, this ball of gas, as it revolved around the sun under its gravitational pull, you'll see that the matter started pulling up together. We have visited a few aspects of this when we were speaking about the geological timescale also. Nearly 500 million years were spent as far as the Earth's solidifying is concerned. Now, if it is going to take such long a period of time, remember that it gives substances which make up solids eventually an appreciable amount of time to segregate as per their density is concerned. And that is why you'll see that when we speak about the Earth in general, you'll see that the inner part of the Earth is significantly dense, and the outer part, as you come towards the outer part, the density keeps on going down gradually. Okay, on a very broad scale, if we are to speak about the interior of the Earth, I will put this together. Okay, you'll see that we have three major layers, though you are seeing four here. Now, why we refer to them as three and why not four? I'll come to that. But you'll see that the outermost layer of the Earth is a very, very thin layer, and it has a thickness of now this thickness varies. On land it is different, and on water, underwater, it is different. You'll see that invariably what happens is now there is an interesting and important thing that we need to remember, that if you take away all the water from the surface of the Earth, eventually you are going to be left with land, isn't it? It's only because of water, which occupies nearly three-fourths of the surfaces, that we tend to classify it as land and water. Anything above land, water surface, is called as land. But remember that once land and water, or water, came on this particular planet, the type of volcanic eruptions that led to the further formation of the crust, it went into say something that divided the crust into two parts, what is called as the continental crust and what is called as the oceanic crust. Now, what is the difference between the continental crust and oceanic crust? If you see, a continental crust is supposed to be made up of granite. Granite is supposed to be less dense as compared to basalt. Now, where does basalt emerge? Basalt emerges under the water. Okay, all that pressure of the oceanic water that is put on these volcanic eruptions, which take place under the surface of these oceans, you'll see that you have basalt formation. So you can call them as different types of crust: oceanic crust and so to say continental crust, because of the fact that continental crust is supposed to be of a lighter density, and oceanic crust is supposed to be having a higher density as such. And it is because of that that you'll see that the theories of crust formation, which started with Wegener, we are going to do one of them, and it's there that they say that continental crust is different and oceanic crust is different. It basically, the difference is based on the so to say the density of the rock material as such. When you go further interiors, okay, as far as the Earth is concerned, you will see that beyond the 60 kilometers, let us say, towards the center of the Earth, we start having what is called as the mantle. The mantle is supposed to be covering a significant part which makes up the interior of the Earth. Initially, you'll see that based on the density, you divide it in the interior of the Earth into the crust, the mantle, and the core. Of late, and you'll see that with development of technology, there are further divisions of the mantle. Like, say, for example, the upper part of the mantle, which is around 50-60 kilometers as such, is supposed to be in a plastic phase, and this plastic phase plastic phased layer, is in fact called as the asthenosphere. And it is this asthenosphere that plays an important role when we describe and discuss and evaluate the theory of plate tectonics, which is one of the latest theory when it comes to the formation of the Earth's crust as such. Okay, then you go further in, and you'll see that the inner part of the core, one of the most denser part of the core, tends to be divided into two layers. Now, why that is true? The whole layer is called as the core, but this core is divided into two parts: the outer core and the inner core as such. The outer core, because of its pressure generated at that particular level, you'll see that it in fact goes into a liquid. Okay, the outer core is in a liquid format, and as far as the inner core is concerned, once again the pressure is so huge towards the toward the center part of the Earth, that it cannot stay liquid. In fact, it goes back into formation of a solid. And that is why you'll see that core tends to be divided into two parts: the outer core, which is liquid, and of course the inner core, which is solid as such. You see that you can see in the diagram the thicknesses of various layers as such. You'll see that as far as the crust is concerned, towards the bottom, you'll see that it's between 80 and 40 kilometers to thickness. At points, you'll see that it including the continental crust, it goes into 40 to 60 kilometers also. You'll see that as far as the mantle is concerned, it is nearly 3,000 kilometers in. Now you'll see that the radius of these spheres is nothing but the thickness of this particular layer. The outer core sorry, is around 2000 kilometers, and the inner core is around 1300 kilometers. So the outer and the inner core together would be nearly 3500 kilometers. But because they are towards the inner part, you'll see that the size is less, and that is why it is believed that the mantle occupies a significant part of the Earth as such. Okay, now coming to how do we read into this aspect as such. Okay, the structure of the Earth. Okay, you'll see that before we go here, you'll see that interestingly, atmosphere has been written there, and the thickness of the atmosphere is 480 kilometers. Normally, when we draw, this is again a misnomer which we tend to have as far as geographic diagrams are concerned. You'll see that whenever we have this films and exaggeration in films, we call that as cinematic liberty. I would call such liberties taken up here as geographic liberties. You'll see that the atmospheric layer is shown as very, very thick as compared to the Earth. But remember that in actual sense, if you go by the scale, the thickness of the actual atmosphere is 480 kilometers. You'll see that, of course, there are going to be various versions as far as thickness is concerned. You'll see some scientists say that actually the thickness of the atmosphere goes all the way to 29,000 kilometers, while others say that it would not be more than 100 kilometers. So there are various variations. These variations, let me tell you, are dependent on how those scientists are looking at the atmosphere. We'll speak about that when we speak about it in the next chapter. Let us not go into that aspect as such for now. We are supposed to be discussing the structure of the atmosphere. The reason I went into the atmospheric aspect is to understand that the thickness of the atmosphere is 480 kilometers, while the radius of the whole Earth is 6,500 kilometers. So that is something that we have to keep in mind and understand overall. Then, as far as the oceans are concerned, you'll see that the center, you can see you have the continents, and around the continents you have around the continents you tend to have the oceans also. Okay, but you'll see that the continents have a base here. Just like we have seen in the figure towards the right of your screens, this screen also, the figure towards the left is now divided into many layers. In fact, you'll see that the mantle here is divided into the upper mantle and the lower mantle. And of course, the upper part of the mantle is further subdivided into what is called as the asthenosphere. We are going to go into the details of each of these one by one, but you can see that as far as these divisions of how do we divide this, okay, this is, as I said, that it is dependent on the density. You'll see that the inner part of the Earth is obviously more dense, and the center of the Earth approximately is 6,371 kilometers from the average surface of the Earth. This will differ a few kilometers here and there if you are measuring. Please remember, if you are measuring the center of the Earth from the say the deepest part on this Earth, and that is the Mariana Trench, or you go to the Mount Everest, top of Mount Everest, and then you tend to calculate what is the distance all the way to the center of the Earth. Okay, there could be minor variations, but on an average it is around 6,371 kilometers as such. You can see here towards the right side, these labelings towards the right side, you have labelings on both the sides. You have it towards the left and towards the right as such. Okay, you'll see that normally you have the lithosphere, which is basically the continental crust, the oceanic crust, and the upper part of the mantle that is called as the asthenosphere. All put together is called as the lithosphere. You'll see that just below the lithosphere you have the rigid crust and upper mantle. So the thickness of a lithospheric plate normally is supposed to be 100 kilometers. Now, why does this word lithosphere come into prominence? You'll see that till this word lithosphere was identified in the theory of plate tectonics, nobody referred to lithosphere as a plate of 100 kilometers. Everybody was speaking about the crust and how the crust is moving and so on and so forth. It was for the first time around 1940s and 50s that the scientists who together propounded this theory of plate tectonics said that it is not only the crust that is moving. In fact, there is some part of the upper part of the mantle also which tends to move around with this, and that is called as the asthenosphere. And the total of say 40 kilometers of the asthenosphere and 60 kilometers of the crust altogether, making a thickness of around 100 kilometers, which forms one lithospheric plate. And it is these plates which tend to move into each other, move away from each other, leading to various types of landforms like rift valleys and fold mountains and all that. Okay, it's the latest, I would say, agreement as far as this theory is concerned, of crustal movement is concerned, is that it is these plates of 100 kilometers of thickness each, and not only the crust. So that is the significance of the word lithosphere, and why asthenosphere has to be taken into consideration along with that. Then we come to the left side of the diagram, the crust. The thickness varies from 3 miles to 4 miles, that is around 8 kilometers. Under the oceans, it is as much as 32 kilometers. Under continent, it consists mostly of granitic and mafic silicate rocks. I told you that as far as continental crust is concerned, it is granitic, and it is less dense. And we are going to speak about this density when we go further into these aspects as such. Okay. Then we come to the layer just below the crust, and that is in fact called as the mantle. Okay, mantle, you can see here, it consists mostly of ultramafic silicates. Okay, silica is one of the most important aspects. I forgot one thing, that as far as the crust is concerned, the crust tends to be further divided into two layers. Okay, the upper one, which is very, very light, is called as the sial, and the lower one is called as the cyma. Okay, as far as the sial and the cyma are concerned, these words are formed out of these so-called abbreviations of these terms. Sial is Si, that is silica, and Al, that is aluminium. So Sial is made up of silica and aluminium, which are the major components, and cyma, silica and magnesium, are two aspects. So what is common in both of them is silica. Okay, so silicates tend to be a major forming element when it comes to even life bodies, as far as the crust and above the crust is concerned. As far as the lower mantle is concerned, it is supposed to be more rigid than the atmosphere. Than the asthenosphere. Extremely sorry, than the asthenosphere. That is basically because of the great pressure that you have. Okay, then you have a boundary. We are going to come to those boundaries between all these individual layers and what they are called. Okay, one thing you have to remember is most of them are called by the name of the scientist who tended to discover these boundaries as such. So that's one thing that you can keep in mind when you are required to remember these aspects as such. Okay, the outer core. Okay, you'll see that is in a liquid phase, while the inner core is supposed to be in a solid phase, and it is significantly rigid as well. Of course, we are going to discuss a lot of things, and that is why we'll move on to the next diagram of the interior of the Earth. Okay, so you'll see that here you can see some details, and more importantly, you'll see that we have named the discontinuities. That discontinuity means continuous and discontinuous. As you go from the surface of the Earth towards the interior, for a particular level, you'll find similar type of rocks. Then those types of rock discontinue to be in existence. And that plane along which you can, in this diagram, you can call it a line, but that plane, okay, because it's 3-dimension, that plane along which the change takes place. Okay, the earlier rock discontinues to be there, and you have a new rock. That is why these are called as discontinuities. And it's on these densities that you'll see that these earthquake waves also change their path here and there, and that is why these are called as seismic discontinuities. the discontinuity between the two layers of the crust, okay, the Sial and the Sima, okay, the upper is Sial and the lower is Sima, is called as the Conrad discontinuity, the Conrad, C-O-N-R-A-D, Conrad discontinuity. This is an internal discontinuity. Let me tell you, the crust is one unit, and within the crust you are going to have two. You have to remember them in that way also. In fact, that makes it understanding easier and remembering easier also. The fact that the crust is further divided into two layers, and these two layers are in fact separated by what is called as the Conrad discontinuity, which lies between the upper and the lower crust as such. Then you'll see that when we move from the crust to the upper mantle, once again, of course, because there is a difference in the density of rocks and the composition of the rocks, you'll see that we stop calling it as the crust and we start calling it as the mantle or upper mantle. So obviously, once again, you're going to have a discontinuity here. This discontinuity was discovered by a Yugoslavian scientist called as Mohorovicic, as it is called, but because it's a tongue twister, you'll see that internationally it is called as the Moho's discontinuity. Okay, he identified this discontinuity between the crust and the mantle. Okay, here it is written upper mantle, but the first difference of major crustal or layers of which make up the interior of the Earth from the crust to the mantle is called as the Moho's discontinuity. Now, as I said, that the mantle is further divided into two, the upper mantle and the lower mantle, and there is a slight variation in the rocks as far as the upper and the lower mantle is concerned. And again, you're going to have a discontinuity here. The discontinuity between the upper mantle and the lower mantle is called as the Repetis discontinuity, R-E-P-E-T-T-I, Repetis discontinuity. You'll see that this discontinuity is interesting because, as I said, the upper mantle is more of it's neither a solid, it's neither a liquid, it's something between that, and that is why it is referred to as a plastic thing. And you'll see that all these helps in the continental plates moving here and there, and we have to remember it with that sense as far as studying the interior of the Earth is concerned. Then you go further down and you come to once again, you shift from one particular layer to other. In the sense, now you are going to shift from the mantle to the outer, to the core. Now, why the core is not intensively called as one core? We obviously know the reason, that it is because of the fact that you have this, different phases of matter. The outer core is liquid and the inner core is solid. It's only because of the fact that the composition, the mineral composition of the core is same. That is why it is called as core. Okay, otherwise they would have named the outer core as with a different name and the inner core as a different name. But because the constitution is the same, they call it all of it core, but the phases are different. One is liquid, one is solid. That is why one of them is called as an outer core and the other one is called as a liquid core as such. But before we go into the core, we have to see this variation which comes up between the mantle and the core. That is called as the Gutenberg. Gutenberg, you'll see by the name itself, he is a German seismologist, and he let us know, or let us say he discovered this discontinuity between the mantle and the outer core, or the core overall as such. And then finally, the last of the discontinuities, which is basically between the liquid part of the core and the solid part of the core, that's the outer core and the inner core, is called as the Lehmann's, L-E-H-M-A-N-N, Lehmann's discontinuity, which, as I've just said, it's between the outer core and the inner core as such. Okay, let us go into a few more interesting aspects, but we'll take them up one by one. Okay. Just give me a moment till I trace my... I'm not able to trace my arrow because of the lights here, but I'll try to put it this way. And this is the interior properties of the Earth. Okay, you'll see that the major um I say classes or the layers of the Earth are included as the crust, the mantle, and the core, and the property. How much of the first property? Let us say what fraction of the Earth does this constitute? You'll see that the crust, because it's very narrow, it's maximum it's 50 to 60 kilometers. It occupies less than 1% of the mass. Another reason why it occupies less than 1% of the mass is of course because of its density. The density is less. I did mention earlier that the mantle occupies a significant portion of the Earth, and that is nearly 70% of the Earth as such, leaving behind around 29 or say nearly 30% of the rest of the portion of the Earth, fraction of the Earth, to be understood as the constituent material, let us say, as far as the interior of the Earth is concerned. Now, the second characteristic is about the state. The second property is the state. How, in what state do we have the crust? It is in the form of broken rock. You'll see that it's broken into small pieces and so on and so forth. The mantle is plastic, of course. We call it as plastic because the upper part is plastic. As you go further down, it is a bit rigid as compared to this. And then as far as the core is concerned, the state, we say the outer one is liquid while the inner one is solid as such. At what depths do you find this? As I said, the crust is around between 30 to 50 kilometers. Okay, I still insist that though it is written here, I would still insist that it is between 30 to 50 kilometers. The mantle, it ranges from around, now these are approximate numbers for us to understand. Okay, you'll see that we can remember this in multiples of 30. 0 to 30, 30 to 30. Actually, it is said to be around 2,900 kilometers thickness, but we can say that it's 3,000 kilometers as such. And from that 3,030 all the way to 6,300 kilometers or 6,400 kilometers, you have the core. Okay, so that is the depths of these things. Now, coming to a very important part, because that's how the physics of the Earth is understood, the density of these layers. Okay, of course, the uppermost layer is the least dense, the crust. The average density of the crust is 2.7. Of course, the Sial and the Saima are again going to have variations. The Saima is going to be a bit higher than 2.7, while the Sial, okay, is going to be a bit lower. It's around 2.5 grams per cubic centimeters, while the Saima is around 2.9 grams per cubic centimeter. As you enter the mantle, the density picks up, and you'll see that it's between 3.5 grams per cubic meters to 5.5 grams per cubic meter. And by the time you go to the core, you'll see that the material making up is so heavy that it makes the core one of the most dense materials as such. And that is why you'll see that the density is 10 to 12 grams per cubic centimeter as such. So that's an interesting and a huge amount of density when you compare it to the mantle and particularly the crust as well. The average density of the Earth is supposed to be around 5. Okay. Now, in fact, it was this density and the calculation of the density from the surface which initially led scientists to believe that the crust does not extend much deep into the Earth, because with these mechanical things, they tried to assess the average density of the Earth, and they found that the average density of the Earth is around 5. Now, they said that if the average density of the Earth is seen to be 5, however, the upper layer is 2.5, and when you go deeper, it is around 2.8, 2.9 as such. This definitely indicated that probably, as far as the interior of the Earth is concerned, it was supposed to be more dense. That is how, in fact, they came to a conclusion that the interior, because nobody had traveled to the center of the Earth, right? And and thus it was very confusing to know that the average density of the Earth is 5. However, the average density of the crust is much lesser. In fact, half of 5. So that was logically indicating at the fact that probably, in fact, the interior of the Earth was supposed to be more dense as compared to the other parts, the outer parts, let us say. When we come to the chemical composition, as far as these layers are concerned, I already said that the outer layer has a lot of silica, and that is why you'll see that majority of the crust is in the form of various forms of silicates. That silica and oxidized silica is called as a silicate, and that is silicate as such. When you go to the mantle as such, okay, you'll see that it is ferromagnesium and silicate. Now you'll see, interestingly, uh, the two sides of the mantle. One side you have crust, and the other side you have the core. Where you have the crust, you have silica. Where you have the core, you have ferrous, and that's iron and nickel. And you'll see that the mantle is somewhere in between. It has some part of iron, some part of magnesium, some part of silica oxide. So it's a transitional zone of from the outer part of the layers of the earth and the inner part of the layers of the earth as far as temperatures are concerned, we can obviously see that the temperatures are going increasingly high as far as the center of the earth. That's basically because of the pressure that you have, okay, towards this. But remember that this is not degrees Celsius, this is Kelvin, and that is why I'm not going to into the details of these numbers, because these are mentioned in in degrees Kelvin, and we are not supposed to be doing it in degrees Kelvin. We would be doing it in degrees centigrade. When we have a lecture tomorrow, I'll get the numbers as far as these degrees centigrade also are concerned, as it's somewhere around 5,000 to 6,000 degrees centigrade as such. Okay, but we'll wait till tomorrow till we get the authentic numbers as such. Then something which is very important is pressure. Pressure is measured in atmosphere, in the sense that one atmosphere is basically the weight of the whole layer of the atmosphere that we have on a unit area. So if we have an area of 1 meter by 1 meter, okay, that column of air of 1 meter by 1 meter all the way up to the limit of the atmosphere, how much weight will that particular thing have on the surface of the earth? That is called as the as one particular atmosphere. And of course, gravity has a major role to play when we understand this in the form of atmospheres as such. And thus, you'll see that as you go towards the interior, obviously the upper layers will have their pressure on it. In the crust, you have this pressure from one atmosphere that's right at the surface, and as you go deeper, you come to the limit of the crust, that's around 50 kilometers as such. By then, the possible pressure would be 1,000 atmospheres as such. You will feel that there are 1,000 atmospheres on you, okay, over you rather, I would say. And that is how, and that would feel a huge amount of pressure, let me tell you. 400 to 500 atmospheres is the pressure of water at the say bottom of ocean basins. So it's nearly double of that by the time you reach the end of the crust as such. Then you'll see that the pressure increases tremendously. You'll see that it literally multiplies as far as the mantle is concerned. That is, from 1,000 atmosphere, it goes to 1,000,000 atmospheres. Remember, 3 zeros, 1,000, 6 zeros, million, 9 zeros is going to be obviously billion. But here it's 1,000 atmosphere to 1,000,000 atmosphere. So by the time you go to the deepest part of the mantle, you could be having a weight of around 1,000,000 atmospheres at your back or at your head. Of course, this is an hypothetical condition. It is impossible for us to sustain. Anything could be crushed under such huge pressure as such. Even the hardest material could be crushed because of this pressure. And by the time you go to the core, you'll see that the pressure does not increase. In fact, it eases out a bit, but still it is higher as compared to that in the mantle. You'll see that 1 0 tends to get added. Okay, you'll see that from 1,000,000 atmospheres, I would say it's between 1,000,000, and let us use an Indian term here, that's between 1,000,000 and 1 crore atmospheres. Okay, so 1 crore layers of atmosphere would be on you, on the top of your head, if you are looking at it from if you're looking above and trying to look above, as far as standing at the center of the earth is concerned. So this is as far as these layers are concerned. Now, because there's this diagram that I wanted to show you, and then I want to discuss on this. I'll not go into the details of that. I'll just bring it to your notice that when we speak about the entire earth that is towards the right, and we identify the various elements that make up the entire of the earth, you'll see that the ranking is iron, oxygen, silica, magnesium, nickel, sulfur, calcium, aluminium, and all the others make just 1%. However, when you come to the Earth's crust, only the crustal part, and there is where human beings live. So we have identified it separately, and we learn it separately as well. Here you will see that oxygen, which was second number, here comes first, and in fact, silicon comes second, aluminium comes third, and iron, which is first here, in fact, drops down to number 4. So we have lesser amount of iron, you would say, in the crust as compared. And this is so very logical when we say that the core is basically made up of iron and nickel. In fact, nickel, which ranks fourth or rather fifth here, hardly ranks anywhere as far as the crust is concerned. In fact, iron is followed by magnesium, calcium, potassium, sodium, and others make up another 2%. So you'll see that sodium and potassium, which are salts, are found in the ocean. So that makes up the crust. Calcium, you'll see that our bone structures are made up of a lot of calcium. So, and you'll see that overall, you have only 1% of calcium, but in the crust, you have 2%. That means towards the interior, you have lesser amount of calcium. I just wanted to discuss this. We are going to go into the details and the other aspects of trying to logically understand what are the elements which make up the interior of the earth when we meet tomorrow. And that's why I'm going to stop here today. And we'll just close this down, and let me speak to you again. Yeah. So if you have any questions for the day, I'm trying. I would be closing a bit early today. Because I see a very less number of students. I don't know what is happening as far as the attendance is concerned. Of late, I've seen it to be dropping significantly, maybe because of Diwali, but that is not the way, because you students tend to lose a lot of things when we are actually speaking or conducting our lectures as such. It was as high as 80 before the Diwali vacations, but it has gone down. So it's come to 25%. Actually, 100% is much more than that. But then of the 80 attending, I have only 20 now. So the number has gone down. Of course, I should not be scolding you all. You all have been attending regularly. But those who would be watching it later, possibly because they get to see this later, because when I come back, the number of views have seem to increase. So that could be another reason why people are not attending live lectures. But anyway, if you have any questions, yeah, there is this question by Bahar. He says that, sir, could you explain lithosphere and asthenosphere again? Yes. I would say in statistical sense, I would say that asthenosphere is a subset of lithosphere. I'll put it the other way. When we speak about plate tectonics, the theory of plate tectonics, of crust, and so on and so forth, we say that one plate is equivalent to 100 kilometers, and that plate of 100 kilometers is called as a lithospheric plate. However, we see that when we speak about the crust, it is only 50 kilometers. The rest of the 50 kilometers has to be made up of the upper layer of the mantle. Now, this upper layer of the mantle, okay, the first 50 kilometers, not whole of it, the first 50 kilometers of the upper mantle is plastic in nature, and it combines itself along with the whole process of these continents moving and drifting and here and there. And that is why when we study about the continental move, we refer to the theory of plate tectonics. And when we refer to the theory of plate tectonics, we always say that, well, as far as this theory is concerned, it is the plate is made up of, it's all dependent on the lithosphere. And the lithosphere, which is a plate of 100 kilometers, includes half of it as the crust, and the rest of it is, in fact, the upper layer of the atmosphere, of the upper layer of the mantle as such. Please remember, within the lithosphere, you're going to have two discontinuities: the Conrad discontinuity, which is between the Sial and the Sima, and the Moho's discontinuity, which is between the crust and the upper mantle as such. So this is something that we were supposed to be, I was supposed to be answering as far as a question is concerned. Well, if you have any other questions, I will take that, or as I said, I would be leaving you all 5 minutes early today, and we'll continue with the elements which make up the crust separately and the earth separately, the whole earth separately. Sachin, Bhosle is referring to, just a minute. Sachin Bhosle says, why core is in a liquid state even if the pressure is very, very high? In fact, the high pressure makes it liquid, and the higher pressure actually makes the core of the earth as solid as such. Okay, you'll see that I could give you an example of an ice cube. If you take an ice cube and you hold it in your fingers, you'll see that if you just hold it in your fingers, it will not melt. But you'll see that if you put it in your palm and you pressure and you close your palm very hard, what are you doing? You are applying pressure, isn't it? So it's because of that pressure that ice cube starts letting water quickly. Okay, earlier it was a small drop, one by one, and particularly when you are keeping it in normal temperature. But if you try to hold, if you hold a cube within the freezer conditions, you'll see that nothing much happens. But within the freezer, if you're going to close this, your fist or your palm, and you're going to apply pressure on that particular ice cube, you'll see that even in those conditions, uh, we can see that the ice cube is losing water, and that's a very similar thing. The thousands of atmosphere, the millions, okay, the 1 million atmosphere, we said that pressure, in fact, when applied to the outer core, it melts the whole of the outer core, and that is why the outer core is in a liquid format. But as we go further down, it again increases 10 times, and that pressure, because it's a center, it's the center of the sphere, you have pressure from all the sides, remember, and this pressure from all the side redirects the center of the earth to be transferred into a solid ball as such. Okay, so that is why the outer core is liquid and the inner core is solid as such. He continues with one more question saying that please repeat plastic state of mantle. Now, plastic is see, when we are using this plastic, okay, when we use plastic, how is it? You'll see that it's not very hard. At the same time, it's not very soft also. So it's not flowing like a liquid. At the same time, it is not holding like a solid. And that is why state between solid and liquid, with reference to the Earth's interior, is supposed to be called as a plastic state. Neither a solid, neither a liquid. Partial solid, partial liquid. Anyway, you could be saying that, okay, can be called as a plastic state as such. Okay, not in the literal sense. Now you would say, sir, I have a plastic chair at my place and it's solid. That plastic is different. Okay, I'm referring to a normal plastic. Say for example, a carry bag. You'll see that it's not as hard as a solid, and of course it's not as light as flowing as a liquid also. Bahar comes up that saying that, but our hand is warm, and when we cover the ice cube with it, it automatically melts. Doesn't it have more to do with our body heat than the pressure? I would say that the body heat would account for only 10%. 90% is going to be the pressure, because you'll see that when you keep, if you keep your palm like this, and when you keep the ice cube on it, it would certainly take much more time to melt totally as compared to when you close. Okay, so pressure plays an important role. Yes, you are right when you say that body temperature, and exactly body temperature is going to account for that as well, but it's a very small percentage that of when we speak about the body temperature. More of this melting is caused by, obviously, when you're going to apply pressure as such. Okay, that's what I feel as far as this whole issue is concerned. So that is as far as major questions were concerned today. uh, if we don't have any more questions, I will just close the broadcast for the day, and of course we'll be continuing tomorrow as such. Okay, that's all for the day. Thank you very much.